כאן אני מגיע בנו. Hi everyone, it's a great pleasure to have Yonatan Givon with us from Weizmann Institute. Yonatan did his undergrad and master here, and then a PhD in Weizmann Institute, and he's about to graduate soon. Great pleasure to have you.
Thank you. So hello everyone, I'm very excited to be here. I wanted to give the climate to give a talk in this seminar ever since I've been a student, and I didn't get a chance, so very happy to be here. So I will today discuss about my part of my PhD work. Hi, לא פספסת. And this branch of my PhD work is focused on Mediterranean cyclones, and I will show you a certain classification framework that I've come up with to analyze actually the cyclone drivers, right? the processes driving cyclones in the Mediterranean. So, for starters, this is the Mediterranean region, and what I want you to focus on here is the topography surrounding the basin. So it's a very complex topographic structure with, of course, the Alps in the north, and we have the Atlas Mountains in the south, but also the geometry of the basin makes it ideal for cyclone development. So we know that this is a very frequent region for cyclogenesis. And of course, most of us are probably familiar with the fact that these Mediterranean cyclones drive most of the weather patterns in the region, especially precipitation, but also temperature variations and other extremes. And what we want to do here basically is try to characterize a typical Mediterranean cyclone in order to improve our understanding of the predictability so that we can reduce property damages and the other results of not well predicted cyclones. So, we know that for this talk I'm defining Mediterranean cyclones as just as low pressure surface systems, weather systems. So that's any system with a closed sea level pressure isobar basically is considered a cyclone for this. Attempts to characterize cyclones in recent decades, or past attempts to classify these cyclones, really show the large variability between different individual cases. And when you compare Mediterranean cyclones to global works done on exotropical cyclones, Mediterranean cyclones really stand out as a distinct subset of the cyclones with properties that range from extratropical cyclones to subtropical cyclones, and even recently the increase in tropical-like Mediterranean cyclones. And I'm showing here the various impacts that these cyclones may achieve. In Israel, for instance, we have, remember the very intense dust storm. I think it was back 2013, if I remember correctly. No. Data. And we have the Alexa storm in 2013, the snowstorm in Jerusalem, the flooding in northern Israel, this is from Nahariya, and of course also sharavlos that give us very warm and dry weather are also, for this analysis, considered as cyclones. Okay. They also show cyclonic circulation, so we consider them as cyclones. And while we know that there are various sorts of extreme weather impacts that are associated with cyclones, it is difficult when you look at the climate scale, it is difficult to differentiate between the different hazards related to differently driven cyclones. So this motivates the need to classify the types of cyclones from a more dynamical perspective, not just what season and region they appear in, but also something about their driving processes and their surface impacts. So why is it so challenging? On the weather scales, Mediterranean cyclones, again, like I said, they can differentially drive extreme rainfall, wind speeds, and cold and hot spells. So it doesn't have to be everything together. It can be separate, or it can be, again, it could either be cold or warm, We can have even dust events that interfere with the cyclone formation and various impacts. And this makes the Mediterranean cyclones challenging to predict. On climate scales, we know that the region is very sensitive to climate warming, and at the large part, this is associated again to variations in Mediterranean cyclone behavior. So the drop of the frequency or the duration or precipitation intensity, etc. These kind of variations over time might produce different climate feedback in the region. However, if you want to really understand how Mediterranean cyclones are going to respond to changing climate, you have to consider the different driving mechanisms. For instance, a good example is that recent increase in medicanes, which are again tropical-like cyclones, that are suggested to be linked to the warming, to the rise in surface temperature in the region. Right? So this is kind of even though climate projections show that cyclones in the Mediterranean should be decreasing with time because of the poleward shift of the storm track, we do see that some of these storms actually become more intense due to this specific deepening mechanism. But it's not just medicanes that are, it's not the only forcing that can change. So we're going to look at the different drivers. But before, I want to show you the previous, some of the previous work, or one central previous work that was done on the classification of Mediterranean cyclones that is not from a geographical or seasonal orientation, because most of the previous works are geographically and seasonal based. So they basically take all the cyclones and say, well, where do we have the cyclone, in what season? This is how we classify it. If it's above Cyprus, it's a Cyprus low, and if it's in the summer in the south, then it's a Sharav low, etc. But Campins in 2000 suggested to look at the cyclone-centered perspective to try to highlight the dynamical understanding, or to increase the dynamical understanding of the different cyclone deepening mechanisms. So he used sea level pressure patterns, but he used a rather limited geographical and also temporal extent, so just 3 years of analysis, and only on Western Basin. And he does get this very nice separation between different mean sea level pressure patterns. But when we look at the projection back to the geographical space, we really see that it pretty much converges back to geographical separation. And even in the paper itself, the discussion of any dynamical insight about the drivers of these different clusters is not really, it doesn't get much far away than just seasonal and geographical considerations. But we know that different cyclones that are similar, for instance, in the thermal features, can appear in different regions and in different seasons, and also very different cyclones can appear in the same region and season with very different impact. So we want to analyze it from a point of view that is not limited by the geographical or seasonal considerations. So the cyclone tracks that we use in this work were produced by Emmanuel Banos, who was here several months ago, I think. He gave his talk about about Mediterranean cyclones. He basically devised a novel approach to cyclone detection, because it's not trivial. It's not a trivial fact that many different cyclone detection methods really come up with different results. They don't converge exactly to the same cyclone tracks eventually. So what he did, he grouped these 10 different cyclone detection methods. Each of them is a robust technique on its own, stands on its own, but he required an agreement between different methods in order to produce a more robust cyclone track data set. And we used here one of these cyclone track data set that has a confidence level of 5, meaning that at least five methods agreed on the detection of a cyclone in each time step of the cyclone track. So this gives us very high confidence in our data, in our detected cyclones, that they are really impactful and not just a short-lived cyclonic disturbance in the atmosphere. And the data includes 3,190 cyclones throughout this evaluation period.
Is it just with subject location?
Right. And on the map I'm showing here, both three density plots overlay each other. One is the genesis region, so it's a logarithmic color scale, so the density corresponds to the brightness of the region. So you see that most cyclones by far initiate in the Gulf of Yonatan and in the lee of the Alps. However, some of them appear in the lee of the Atlas, in the Black Sea, and other places where they can originate. The peak time is shown in red, the density of the peak time. So most of them, many of them get to their minimum SLP very close to their initiation location, but others can propagate quite far away. And the termination stages are much more dispersed over space, so it's hard to tell, but they also, we see where cyclones tend to terminate. So in this region here, in this region there, this is where the cyclone, on average, all of the cyclones that we have, this is where they tend to start, peak, and dissipate.
You don't differentiate between cyclones with a very low SLP and say just slight variation
No.
in SLP.
No, I will allow this to be the result of my classification, basically. Okay, so like I mentioned already, there are several processes that drive Mediterranean cyclones. And each cyclone can be forced by a combination of them. It doesn't have to be a single process that drives a cyclone. But it's kind of a first order assumption that we made in this analysis. We assumed that for each cyclone trap, we could possibly detect a dominant mechanism for its deepening. So what are the forces that we're looking at? And of course, this is just a cloud satellite image that shows a very nice Mediterranean cyclone here, with dry intrusion coming to the north and spiraling inwards, creating this nice cloud spiral. And I just want to go through the known, like what is known from literature about what drives these cyclones, not only Mediterranean cyclones, but cyclones in general. In the Mediterranean, there are some extra forcing, let's say. So first is the adiabatic process. Of course, upper level PV advection. This is in the Mediterranean. This is seen as the most dominant contributor to cyclogenesis and cyclone deepening. Diabatic processes, so latent heat release by condensation in the middle of the troposphere, is often described as a slightly different mechanism. Basically, it generates PV in the mid-tropospheric level. PV, like saying PV, I'm talking about potential vorticity. For those who are less familiar, I will go over it quickly in a minute. We have the release of potential baroclinic instability or genesis, so the kind of classic Scandinavian model, right? Where we have a baroclinicity and the cyclonic motion starts to create fronts, and this gives us the more baroclinic oceanic cyclones. We have heat lows, again, just warm surface temperature anomalies that generate local convection, can grow into a cyclone. We have data lows, which are systems that are formed downstream from another more synoptic scale cyclones. So they are smaller cyclones, very typical for the Mediterranean. It's been thoroughly studied by our Zida's group, Tel Aviv. And we have, on top of all of that, we have topographic modulation. So, like I mentioned before, the presence of mountains of topography creates blocks for the flow in one sense, and it creates channels through which the flow can actually accelerate on the other hand, like in the Mistral, in the case of the
categories have mechanisms except for the daughter.
Sorry?
All mechanisms have mechanisms except for the daughter. What is the mechanism for that? How is it distributed?
Okay, so I will address that in a minute, but this is considered to be a separate kind of phenomenon. When you have a large-scale cyclone and in its outflow you have a smaller cyclone that appear really
so
next.
is it photogenesis?
Not really. I will show some figures about this also, but what I see mostly happens is that the synoptic scale cyclone generates a very intense warm sector, and in this warm sector you have the generation of a small heat low, basically. But again, this is different than another type, than the classic typecast of Sharav laws that we know. This why I want to address them differently, and they also, you will see in a minute that data cycles also, well, they just emerge spontaneously from the analysis that I made. Okay. This is the PV, I will do this again if it was too fast. This is I'm overlaying the PV structure, the upper level potential structure over this cloud figure just so you can see the high correspondence and why I say that upper level PV really control Mediterranean cyclones. See this very nice high values of PV coming in, spiraling towards the surface cyclone. This is SLP contours in black, in 2 millibar differences, topography in gray, so you see that the streamer kind of has to go around topography in order to get to the surface cyclone, and the shading is upper level PV distributions, which I will discuss right now. So for those of us less familiar with potential vorticity, the classic relationship between the upper level atmosphere, the tropopause basically, and the surface weather. Well, what is the classic paradigm? We have a lowered tropopause corresponding to a positive PV anomaly. This generates cyclonic circulation in the upper levels and induces also uplifting and circulation in lower levels. And then these cyclones are expected to propagate together towards the place where the air is rising, and they can live like this as baroclinic cyclones. However, in later stages, as the cyclone deepens, we actually see from theory that, and also from observations, that there are two distinct life cycles or two options for this wave to take towards its evolution to later stages. One path would be anticyclonic wave breaking, or like Tom Prophet noted it, life cycle 1. In life cycle 1, we see a growth of the surface cyclone to a point where the PV streamers begins to deform and to overturn. We have a reversal of the PV gradient, the meridional PV gradient. If the reversal is towards the back of the trough, this is PV contours, and this is SLP contours in response to the upper level PV contours shown here. If the PV contours, the overturning is in the western part of the trough, then this will be life cycle 1, and this will lead to a very distinct behavior of the cyclones that are noted here, and the ridges or anticyclones that are associated to this specific PV breaking pattern. However, this is just one life cycle. The other one, noted as life cycle 2 or cyclonic wave breaking, is where the reversal of the PV gradient occurs east of the trough of the maximum PV anomaly. And in this case, you see that the cyclone behavior would be much, much different. They will be much larger, much deeper, and they also will persist for longer and retain their kinetic energy for longer time, considerably longer time scales. And this basic paradigm of what's the wave-breaking life cycles has rarely been addressed with relation to Mediterranean cyclones and how it affects them. And this is one of the core ideas of this work, is to try to look at PV distributions as indicators of different drivers. But it's not just Rossby wave breaking. These are just two different manifestations of upper level PV advection, right? But there are, again, like I said, there are other mechanisms as well. So what we aim to do with this classification is basically to construct a conceptual process-based cyclone classification framework. We expect it to distinguish between cyclone track features and different surface impacts associated to each cyclone track, with the goal to enhance the understanding of MC's predictability both in present and future climates, basically by decomposing this large thing that is considered as a whole as Mediterranean cyclones, decomposing into a spectrum of cyclone driving mechanisms and analyze the data from a new perspective this way. How do we do that? Like I said before, we have these 3,190 cyclone tracks. For each cyclone track, we look at the upper level PV distribution, vertically average between 320 Kelvin and 340 Kelvin isotropes. So that corresponds to the chunk below and the chunk above the troposphere at roughly every season. And we only take the minimum sea level pressure time of each Mediterranean cyclone track, which assumably corresponds to the maximum intensity of the cyclone. We want to classify the cyclone at maximum intensity so we can get the best details about the driver, the cyclone driving mechanism. So we want it at its peak, basically. We use a cyclone-centered perspective, which means I'm taking the field around the cyclone center in a relative manner, not a constant frame in the geographical dimension. And I'm using a self-organizing map technique, which I set for 9 clusters. It's not just a random number I choose. If you want to go up, if you want to, I can go over it later, how I come to 9 clusters. But the idea is again this: we take these 3,000 cyclones, the upper level PV distribution from a cyclone center perspective, and we want to see how they fill up the SOM space, the self-organizing map space, or basically we want to spread their variability so we can see what is going on in these systems.
You use some kind of K-means?
It's very similar to K-means, yes, but I used a different technique. I did both. I used both initially just to compare. The self-organizing map gave a slightly better separation, especially with emphasizing the non-linear system states, so the wave breakings and cutoffs, which we'll see in a minute. But just briefly, I want to show before how the self-organizing map really works. So imagine a random initiation of cluster weight. So these are my SOM clusters or nodes, often termed nodes or neurons, and basically each of them cover a different space in the SOM input. What is the SOM input? Let's assume it's just pixel brightness of some image, and disregard the color. It's just to separate between the different examples. So for instance, if we have a pixel that is bright in this region, it will be associated to this cluster, right? And again, if we have some different brightness in different region, different cluster, etc. What's really interesting about the self-organizing map, though, and not like the K-means, up to here it's K-means, basically. But in this system, what is interesting is when you have actually a geometrical kind of different geometry of the input. When you have a feature that is different than this, the geometry is saved or recorded in this neuron, and this is the node weight, the weight of this neuron or cluster. And the weight remembers the pattern that it had, and then after some more clusters, some more cyclones or inputs are associated to different clusters, you may have a similar pattern in somewhat different place, but our algorithm is smart enough to notice that even though it fits to the location of this neuron, it actually resembles more to this neuron, because the computation of the distance also take into account the topology of the system. So it will associate this new pattern to the same cluster as before, but it will adjust the weight in a way that will now consider more space for this cluster, and again adjust the weight of the node accordingly. And the last step is the update of the other SOM weights with respect to this one, so that it will be slightly more similar. So the other nodes are now taking into account that there is this kind of geometrical pattern, and they try to be slightly more similar to that. How does it look if I look in just 2 dimensions? This is an example. This is the data that we have, just a random distribution of data around some zero center point. And these are the randomly initiated SOM weights. You see that they don't really have any connection to a specific region in the data. However, in few iterations of the process that I've shown here, the clusters can adjust themselves and spread out across the data, and you'll have a situation where you have more clusters in more dense regions with dense data, and less nodes where there's less data, and then this is how this classification basically works. And this results with a low-dimensional representation of higher-dimensional data, right? So we basically look at the temporal variability or the many different examples of this similar phenomenon known as Mediterranean cyclones. We look at many of them, and we want to be able to extract similar, dynamically similar individuals from a certain cluster, right, or a group. And this is already kind of. I'm sorry?
Input is only the PV maps?
For now, yes. For this analysis, the input is only the, like I showed it here. Let's go steps back. So that, yes, this is just this is the input. The cyclone center is here. You crop a field around the cyclone, and this is the only input for this. Yes, for this one, for this classification. So. Yes. So this is how the result looks like on this classification of Mediterranean cyclones. Each hexagon here, the grayish blue hexagons correspond to a single cluster, and the shading corresponds to the distance between them. Like you see before, the distance between these little red dots that spread across the data. And you see that for most clusters, the distance is quite high, so there's no similarity. This is good for me because I want the clusters to be as distinct as possible. And I want to say that unlike the EOF or other methods of this kind of decomposition, here each individual cyclone is associated to a single cluster. Okay, there's no kind of 50% that and 50% that. It has to be one winning neuron. And these clusters are then mapped by the distance between them. So the most similar clusters will be closer together, and the more distant one will be further apart. But still, you see that there is a lot of difference. So these clusters are very similar. We're going to see that in a minute. While these ones are very far away, even though they are neighbors, right? It suggests that other clusters further away are even further away in some space than that. Right. So this gives us a semi-continuous spectrum of the dominant system state. Let's see what it looks like, not in words. This is the spectrum that we get. So in the upper, these are all upper level PV distributions, composites over several hundred cyclones in each of these beams. And this is the overall mean, like the average, the total average for all of the cyclones. On the first look, you can already tell that the total mean does not look anything like any of the clusters. Which means that when you just average, like in climate simulations, you're looking at kind of an average impact of Mediterranean cyclones, you're really overlooking a lot of internal variability. But further, we can already start and see and detect these life cycles that we've mentioned before, and some of the other driving mechanisms that literature suggests. So the most similar clusters were 1 and 4, so you really see the similarity. However, you also see a very sharp distinction, which is very meaningful because it suggests a different stage of least cyclogenesis. So for those of us familiar with least cyclogenesis, it's usually separated into 2 stages. The first stage is the initial rapid deepening of the cyclone, when it is still, the flow is still blocked by the topography. And the later stage is when the cyclone propagates away from the topography to generate a frontal structure. So this is what we get here. But other than this similarity here, we really see very distinct clusters. So we have a very weak surface cyclone here in a rich environment. We have a very kind of slightly stronger PV cutoff. We have a much stronger PV cutoff. And we have both of the Rossby wave life cycles. We have anticyclonic wave breaking here, and we have cyclonic wave breaking regime here. And we have the Dator cycles. So again, we have a very strong synoptic cyclone, which would be clusters 1 and 4. And just slightly downstream from it, we have a secondary cycle for it. So from now on, I will show in title the mechanisms that are associated with clusters.
There is no cutoff.
We mean this and this. It's hard to tell it, but yeah, there is.
Cutoff of PV coinciding with the surface.
Towards the surface. I will show the vertical, I will show it in a minute. Yes, I will show towards how another PV also is impacted all the way through the surface. But yes, I want to again highlight in this opportunity that this classification was only made on upper level PV at a single time of the cyclone track. But we also required, if you remember, that this classification will give meaningful variations in cyclone features, not just in minimum SLP time and not just in upper levels, but in many other parameters. I will show this in a minute. So, firstly, and again, I want to highlight that these are several hundred cyclones in each individual panel here, and to get these non-linear averaging, it's not trivial at all. Okay, it's it's really a big strength of this for the SOM technique. Big advantage. So these are the first features that we're looking at, because I said before that until now cyclones were separated by season and geography, but here the geoseasonal variation also comes into play, but it's not directly forced upon the system. Which means that while there are cluster favorable regions and there are cluster favorable seasons, there is huge internal cluster variability that really allows us to tell when we had, for instance, a cyclone that usually appeared over Europe, but once it came here, we can analyze what happens in this case. This would be a highly anomalous case, right? And also we can see that in similar locations, we have differently driven cycles, different clusters, and they can have very distinct surface impact and other features, as we will see in a minute. But I just want to connect to the cyclone drivers that I talked about before. So cluster 1, you see, is almost exclusively initiating and getting to its peak, very tied up to topography, to the Graph of Genoa. So we can associate it really with this first stage of cyclone deepening, the low stage A. In stage B, you see that the red region is already more spread throughout the Mediterranean, again corresponding to a freely more similar to a freely traveling kind of extratropical cyclone in the ocean. Of course, of smaller scale because they're in smaller basin. The other wave-breaking patterns also show very distinct geographical features, but they can occur in various locations and seasons. And of course, the Sharav law, you see that it's very strongly linked to the North Africa. However, it may also propagate further north and drive very extreme weather, like Mediterraneanos, for instance. Mediterraneanos, if you remember, in Greece and also Libya, may wreak havoc throughout the region, was actually classified as a Sharav law that made a propagation towards Greece. So these very warm temperatures generated a Medicane. It's not the only scenario that can generate a Medicane, but if you want, I will go over this later. The second parameter I'm showing you now is again one that is not just concerning the time of classification, the minimum sea level pressure time, but it actually looks at the entire cyclone track. I have the PV here for reference. These are distribution plots of the deepening rates throughout each cyclone track. What I did is I looked at each cyclone track, at each cluster, of course, and I've asked, what is the maximum 24-hour deepening rate that I have for each cyclone track? So it's not associated necessarily to the time of classification even. But if it's above 1, it's considered an explosive cyclone. This generates very, very intense storms. And so you see that really there are variations. And even though, like I said, it was only classified upon one instance in the cyclone lifetime, it really has variations that are projected throughout the cyclone track. So we see very distinct variations, and we see that only some clusters can really generate explosive cyclones, at least in historical data. The next one is very important, also considers the entire cyclone life track. This shows us how different do these cyclones propagate in space. The propagation of the cyclones across the horizontal space is very important because these cyclones are very rapid, going very quickly towards the west, for instance, the east. Like on average, this is showing the average direction and wind speed, not wind speed, the propagation rate in meters per second of each side this is the total average, and this is for each cluster, the deviation from the total average. And you see if we have, for instance, a more static cyclone, one that lingers longer at the same place, it means that also its precipitation will accumulate and to larger values, And also if it brings with it some kind of a heat wave, then also it will be more consistent. So showing these variations in the cyclone propagation is very meaningful to improve the understanding of the cyclone predictability. And it's a very difficult measure to isolate. And if you want, I will show you later that it's not just noise. I mean, each of these vectors is consistent of several hundreds individual members that are all aligned in the same, roughly all aligned in the same direction.
If it is 2 to 10, it goes towards 10 or from to 10?
Sorry?
Is it going 2 or 4?
It's going towards this way. So the cyclones in general propagate towards the west, right? Then it was the east, close to the westerlies, and towards the north slightly because of the beta drift. But we see that individual cyclones can.
Right is north.
This is north, and this is.
What is 0?
0 is west, is east.
It's not azimuth, it's confusing.
Okay, yeah, I mean, I've considered showing it this way, but this is how it's already been published. Yeah, but then 0 is east. In this, so from the west to the east is 0, and this is north.
So you have propagation west as much as propagation east. Doesn't make sense.
No, it's deviation from
This is deviations from this, for each cluster. So for each cluster, I'm showing how differently it propagates from the total average. So you see that these cyclones are slower on average than the total mean. And these ones are quickly traveling. And again, this is the cluster 4, as I mentioned before, which is a freely traveling wave. So it makes a lot of sense. And also, when you have easterlies in upper levels, like in cluster 2 and 8, if you have some easterlies, then cluster 2 is hidden under the cluster 8 vector, but they're very similar. But then you have more slowly propagating cycles. So this all kind of combines, PV really combines a lot of the information about the atmosphere. And now, these are I've just shown some cyclone tracks that are associated to the cyclone as a whole, but now I want to look at the surface features of each cyclone at minimum SLP time, at the maximum intensity. This will also help me to shed light on the different cyclone drivers that I mentioned. So now I'm showing here in shading the total 2-meter temperature anomaly, and when I say anomaly, I mean gridded climatology, right? Monthly gridded climatology. So we expect, of course, if the cyclone is here, we expect a cold sector somewhere here because of the northerlies, and the warm sector somewhere here because of the southerlies in this region. However, when we break it down to clusters, you see that it's really not always the case. It varies very strongly. For instance, cluster 6, the Sharab, of course, very strong. Warm temperature anomalies, no evidence of any cold sector at all. And it's not just because it's summer, right? Because it's gridded, it's because of gridded climatology. So it means that it's even warm compared to the warmest region and season on Earth. Okay? Very intense warm anomalies. The daughter laws also show a very similar story, but with some cold sector associated to the larger cycle. And like we was before, is it a different scenario? So yeah, we see very intense surface temperature anomalies, which are associated to heat loads in the case of these cyclones. And we see again, like I mentioned already, in cluster 4, a very classic almost frontal structure as opposed to cluster 1, even though they were similar, right, from the previous standpoint. We see that in temperature, it's much, much colder anomalies in cluster 1, cluster 2, both. Also warm anomalies to the pole, towards the pole, cold, very cold anomalies in the middle. So you see very sharp deviations. And again, if you want to know for instance, what's the impact of climate change on cyclones and how does this feed back to the regional climate feedback, you really need to know which one of the cyclones you're going to get more, right? But if you're getting more of the very cold cyclones and less of the very warm cyclones, then maybe there is some kind of a negative feedback you can hope for. If it's the opposite, then that might even be concerning, right? So, another very sharply separated parameter is precipitation. I'm showing total precipitation here in shading, and I'm overlaying the convective precipitation. So, the large scale here it's the total precipitation in shading and convective precipitation only in the black contours. Here, the shading is the large scale difference for each cyclone compared to the total mean. This is in shading. The contour is the same thing, but just for convective precipitation. Okay, so I'm showing that what I want to see is not only if we have more or less precipitation, right? More precipitation and less in certain clusters. I also want to see, is it more of a large scale and less of convective, or the other way around? So, the results suggest that for most cases it's both, right? You have your more large scale and more of the sign contour, which is the convective. And overall, it's in black contours here. The overall precipitation is largest in this case. However, in some of the cycles, you actually see less convective precipitation in a region where the large scale is increasing. And we see the opposite, where we have a large scale decrease in precipitation, but a very intense convective precipitation. So again, this shows us there is a separation of different mechanisms operating in this, between these clusters. Again, I'm not saying that each of these drivers is exclusive for all of the cyclone in here, but it's the dominant one that can be detected from the upper level PV. Surface winds are also very important in order to understand the hazard and the associated impact of Mediterranean cyclones. And again, I'm showing the total wind speed 10 meters around the cyclone here, and the deviations. So these are not deviations from this, these are the anomalies. Again, compared to gridded anomalies, this is in shading. So you see already that some clusters have much stronger circulation near the center, while others have much weaker circulation. And I overlaid the PV anomalies, so you can really see this upper level surface coupling. So here in cluster 8 and cluster 2, the PV anomaly at the upper levels is maximum. Right? It doesn't mean that the PV values are large, it's just that the anomaly is greatest. It means that these limos are arriving in regions that are not used to this kind of PV values. So, and we see that the most intense PV anomaly is associated to the most intense surface circulation. And we can even see the jet structure. This is in cyan, the 300 hectopascal isotach of 30 meters per second. You see that even the jet structure is different between these clusters. Or it can even be said that it can also be argued that the PV dictates, right, this variability of the upper level jet. And just to connect to your comment before about the vertical cross-section of the PV, so you see it here, you see that for all of the clusters, almost all of the clusters have a PV anomaly in the upper levels, except for cluster 6. But we see that for some clusters, it actually extends almost all the way to the surface. In other ones, we have only a surface PV anomaly, but nothing in the mid-troposphere. So the mid-tropospheric anomalies are associated to latent heat release from condensation, whereas the surface temperature anomalies are associated with the surface temperature anomalies, right? The generates large PV anomalies. And then this, again, is another argument that supports the separation into different driving mechanisms. And we see the most distinct PV towers, what we call PV towers, which is values of FPV all the way to the surface. In cluster 2, this combined pattern of anticyclonic wave breaking and cyclonic wave breaking in the lee of the mountains. So how can this help us maybe enhance the predictability of weather of Mediterranean cyclones on weather scales? Well, we show here that even if you lag each cyclone back to its genesis time, the clusters are still discernible. This is our PV composites and SLP composites of the same clusters, just lagged back to genesis time. And you see, you can already tell at cyclogenesis what is going to become of each of these cyclones in terms of temperature anomalies, wind speeds, and etc. Precipitation, propagation speed, and everything that is important for predicting these events. So one suggestion that I haven't conducted it yet, but one idea that I have is to try to implement these clusters into weather forecasting and to see if we can somehow constrain the large ensemble spread that often occurs, especially when nonlinear PV evolution occurs in the Mediterranean. And I'm almost getting to the I'm about to wrap up. So, just a very important result, and this was noted by the reviewers of this paper. To the kind of the highlight of this paper is that I'm looking at accumulated annual occurrences for each cyclone. So overall, is here on the black, and you see that there is maybe some intrinsic jump, but it's not significant. Okay, so per year we have roughly between 70 and 80 cyclones per year, and it's roughly constant. But if I measure the same thing per cluster, you see, like I said, mentioned before, a decrease in the winter cycle, as expected, right, from the original shift of the storm track in future climate or in recent years. But a very sharp increase in these warm cycles that are associated to summer and to more southern regions. But actually, I've shown that they are also starting, especially cluster 6. The Sharav starts to appear much further up north and in much later seasons. So this kind of gives us, this implies to an expansion of the tropics, basically towards the north, and the ability of this kind of very dense heat load to propagate further poleward. Yes, so again, like I said, this could be concerning because this means that it's not just that cyclones are decreasing maybe decreasing in future climate, they also become much warmer and much drier, okay, and with less cover, with less cloud cover also. That's very important for understanding the response of the Mediterranean to global warming. So this is almost the summary of just kind of overviewing the cyclones that I've shown, the clusters that I've shown you here. We had cluster 1, a stage A, the Lee cyclone, which peaks still locked in the initial rapid deepening phase. We have the most intense storms, classified as a combination between anticyclonic and cyclonic wave breaking. They provide, like I've shown, they provide the strongest PV anomaly and the strongest surface circulation. If you want, I can discuss this further. We have the long wave cutoff flows, so very large chunks of air that are separated from the main PV reservoir, usually over the Atlas, but can also be in the Black Sea, and they have a very distinct surface impact as well. I've talked about a lot about the state B cyclones, these frontal structures, they're much more quickly propagating. Clusters 5, as expected from literature, the anticyclonic wave breaking cyclones are weaker, tend to be weaker, shorter lived. Sharav lows, most in North Africa, but recently increasing also over Europe, a very concerning trend of basically European desertification. Darter cyclones, they are very rapid, they travel very quickly, they deepen very quickly, but they are of smaller extent, and hence of smaller impact. And the cyclonic wave breaking, probably the stormiest cyclones out of the winter seasons. These ones show the cyclonic wave breaking pattern, and short wave pattern flows. For some cases, this could actually be just heat loads coming from the surface, but generating an upper level signature as they continue to precipitate. And a lot of other features you can see in my paper. So this work really lays a foundation for a climatological analysis of Mediterranean cyclones, and it's already been picked up by the Med Cyclones community. So I will just briefly show some works, some of them already published, that use these clusters. For instance, we saw Ritzi et al. This is an accepted paper, already submitted, already accepted. Looks at the compound extreme. So it's measuring the rate of extreme wind events, extreme rain events. It shows how they vary across the clusters. This is for each cluster, but you see that even though cluster 2 doesn't have the most intense rain or wind, it still provides the highest rate of extreme compound events. So a compound is when the two hazards overlay each other. So again, this again strengthens the link to the cyclone driver here. And quite similarly to this work, another work that uses these clusters looked at the spatial distribution of how much of this compound extreme